also in short IVT. I have to say that the intermediate value theorem has limited applications. If the function is not continuous, we cannot apply this theorem. The function must be continuous. That's why this theorem is together with continuity. The function must be continuous, otherwise it's not applicable. So let's take a look at a function. The very, very important use of this theorem, you will see it in chapter 4. In chapter 4, we will be able to solve any equation that we were never able to solve algebraically. And we can look at any type of equation and we will be able to solve it with any level of accuracy you can think of. If you want 11 digits, it will be accuracy with 11 digits. If you want 100 digits, 100 digits. But we can't do this with algebra. We can only do it with calculus. This theorem will come into play because it will help us find the interval. This theorem will not solve an equation for us, but it will tell us, it will give us an interval in which normally a 1 unit length, not between 0 and 10, but between 1 and 2, or 2 and 3, or 3 and 4. So this theorem will say to us, I cannot solve the equation, but I guarantee you there is a solution between 0 and 1. I cannot solve the equation, but I guarantee you there is a solution between -3 and -2. Without this theorem, we will have difficulties in chapter 4 in trying to solve an equation. And I'll show you an example in a minute. So let's say I have an interval between A and B. And let's say I also have a function. This is our function. And I'm going to ask you 2 questions. According to the graph, number 1, will you say that f is continuous on the closed interval a comma b? Question number 2, will you say that f of a from my graph is less than 0 and f of b is greater than 0? I can have the situation reversed, right? I could have graphed a function like this. It doesn't matter, really, for the purpose of that we're looking at right now. So now I would like you to help me finish up my sentence. Therefore, by IVT, there exists a C, a number called C. This is another symbol that we have not seen before. In the interval, open a comma b, such that f of c, don't say anything just yet, allow me to give you a hint. The function is continuous on the interval ab, and it changes sign from negative to positive, or from positive to negative. Therefore, there must be a number between a and b, between 0 and 1, between 1 and 2, between whatever it's in there, such that f of c is definitely absolutely. So in other words, c is a root or x-intercept of f of x. Indeed. How does this happen? Because the function is continuous and it changes sign on that interval. Yes, please.
Because in order for it to not cross 0,
it should be jump. It has to, exactly. That's why what we quote here is the theorem that on an interval, if a function is continuous, it must be continuous at each and every point. Otherwise, it's not continuous on that interval. So in other words, the function has to go point by point. And it will eventually be 0. This is the IVT. Here's an example. Let's look at problem 53 on page 129. and we have e to the x equals 3 minus 2x. We're asked, use the intermediate value theorem to show that there is a root of the given equation. No one can solve this algebraically. Yes, you can use the calculator. Yes, you can use the software, mathematical software. But no one can solve this, this equation algebraically. No one. There's no way. So the first step is to move everything to one side. E to the x minus 3 plus 2x equals, thank you. Step number 2, denote by f of x this expression, e to the x minus 3 plus 2x. In step 3, we are, in this particular problem, we are given the interval. So we are told 0, 1. This is given to us. It will not be given to us in general. So I will show you an example in which the interval is not given to us. What can I say about the function? F is on 0, 1 as a combo of functions. Which words am I missing?
It's continuous. This combination of exponential.
Okay, that's fine. So let's go back to the checklist.
So it's a combo continuous.
Of course. Negative 3 is a continuous function. 2x is a continuous function. E to the x is a continuous function. Any addition, subtraction, multiplication of continuous functions must be continuous. Step 4. What do you think I will have to show and convince you in step 4? Without which I cannot make any conclusion. I have to convince you that f of so we know the function, we know it's continuous, we know we are given the interval 0, 1, so I have to convince you of the last step, that the function does what on this interval? Changes sign. If I don't show you that it changes sign, then it cannot cross the x-axis. So I have to show you that f of 0 is blah, 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 let's say positive, and that f of yes is right, or the other way around. Agreed? Good. So e to 0 is 2 times 0 is 0. 1 minus 3 is, this is negative 2. Now f of 1, if f of 1 is not, what type of number? Right, if f of 1 is not positive, can I apply or I cannot apply IVT? I cannot. So let's check with f of 1. I don't need the exact number, I just need a sign. So negative 3 plus 2 is negative 1. E to the first power is 2 point something. 2 point something minus 1 is a positive number. That's all I care about. So what do I conclude now? From 1 through 4, by IVT, what? We know for sure that there exists C, in which interval? Very good. Such that f of C is guaranteed to be, that's it. Notice that the theorem does not help us find the solution. It only says, I know for sure there is one,
Somewhere around here.
exactly, between 0 and 1. The function must cross the x-axis. Okay, so let's look at another example in which we are not given the interval, and we have to find the interval. Here's another example. Let's look at 55, in which we have cosine x equals x to the third. Again, no one can solve this equation algebraically. You can solve it using the graphing calculator. You can solve it using Mathematica or my Math Lab or, Math Lab and Maple. But no one can solve this algebraically. What will be the first step? What do I have to do first? Of course, thank you very much. Good. Step 2. Yes, my f of x is cosine x minus x to the third. Step 3. Cosine is or is not a continuous function? It is. X cubed. Is x cubed always a continuous function? It's a polynomial. So then what will I say? F of x is continuous. This is part of the theorem. I have to write this. F of x is continuous everywhere, if you want, everywhere, as a, if you want a difference, now you don't have to say a combo because there is a simple difference, as a difference of what? Continuous functions, right? I have to explain that. Continuous functions. Now in step 4, I have to go to the graphing calculator, put it in y equals, and we have cosine x minus x to the third. Okay. Make sure that the mode is in radian mode. It is. Make sure that second and table set, okay, is still in the ask mode, correct. And I go to second and table, and I have no idea where to start. I'm going to say 1, negative, 2, still negative, 3, still negative. In my case, I do see here the software shows me a graph of that function. So obviously at 0 is positive and at 1 is negative. So I'm going to go back and say 0. Ah, it's positive. 1. Ah, it's negative. I need a 1 unit length interval. I cannot say between 0 and 10. I have to use at most a 1 unit interval. So then I have my interval. What will you say? F of 0 is 1, and f of 1 is negative 0.46. Therefore, I found the interval. So the interval is 0, 1. So from 1 through 4, and by IVT, what do I conclude? I do not know the 0. I do not know the solution, but I know there is one for sure, guaranteed. So there exists a C in the open interval 0, 1, such that f of C must equal
0.
Very good. Is it clear why we did not use any other number or any other numbers for this? I couldn't. All these were positive. So between whatever and whatever, the function doesn't change sign. IVT is not applicable. So I had to find a 1 unit interval in which on one side is positive and on the other one is negative, or vice versa. That's why I had to choose 0, 1. Any questions on this? Is this clear? Okay, perfect. So what I showed you in class, it's a variation of the intermediate value theorem. It's the method, it's the one particular variation of the intermediate value theorem that we apply in solving equations. But I also put the general form here. But what we use is the one that I presented to you. Okay. So let's read 26. We learned how to find a unit length interval. We just did. Or smaller, if we want to, we can find a smaller one, where a continuous function has a 0 using the intermediate value theorem. Just to remember that we did that. We learned how to make a function continuous everywhere. We just did that. No, we didn't. I'm sorry, this is where I'm at right. If it has a removable discontinuity, and that's my next step. So, on the same page, I didn't mean that, sorry. On the same page, I would like to choose a function. Okay, so here it is, in which, using the function we are given, thank you, Joe, in which we are using the function we are given, like, let's say 23, on page 128, and here it is, f of x equals x squared minus x minus 2 divided by x minus 2. It says, let's read the question. How would you remove the discontinuity of f? In other words, how would you define a new function in order to make it continuous at that point? Okay. So first of all, we are given this function. What type of function is it? Exactly. It's a rational function. It has a problem, like many rational functions. What is its problem?
It's got 0 degrees, or
When?
and x equals 2.
Perfect. So x cannot equal 2. X equals 2 cannot be in the domain of this function. Awesome. What do you think will be the next step? I'm looking at this function. Number one, I identify that it's not defined at 2. And then what will I say? What will I do with it? Of course. So let's try and factor the top. How do I factor the top? Very good. What do you think I'm going to do next? But not before I stated the restriction. It's already there. That's my first thought. Domain is the first thought for any function. So I stated that x not equal to. Actually, Tom gave me that. And now what do I do next? Exactly, because I can. I stated the restriction, and now I'm allowed to simplify. X minus 2 divided by x minus 2 and x minus 2 divided by x minus 2. I have to write the 1, so I don't get the impression that it's 0 anywhere. So what is the simplified form of this function? Very good. So here's what we are going to write. By the way, is this function continuous everywhere?
Yes. Yep. Not except 2.
Correct. So this function is not continuous everywhere. It's continuous on its domain. I would have to agree with that. It's continuous on this domain, but since 2 is not in the domain, I cannot say that the function is continuous everywhere. Correct? Perfect. What type of discontinuity is this?
Removable discontinuity.
Exactly. How do I know it's removable? Let's check. How will I know that the discontinuity is removable? Remember what I have to show, that the limit as x approaches 2 from the good, in a moment we'll come back, equals the limit of, I'll come back to that, as x approaches 2 from the right, but it does not equal, right. So remember what the removable discontinuity is. Function values, let me show you the picture. Here it is. Here's the removable discontinuity. The limit from the left equals the limit from the right, but it does not equal the function value at that point. So I have to show, the book says, well, this is removable. I don't know. Let's see. So the limit from the left of what? Awesome. The simplified form. And the limit from the right of what? Of course. So how much is this? Perfect. How much is this? Good. So is this x equals 2, or is this does this function have a removable discontinuity at 2? Yes, because both limits are the same. Now the book is asking us, the problem is asking us to create a new function using the given function that will be continuous everywhere. Yes, please.
Can we do a piecewise function?
It has to, I have to use this. So I will say it's x plus 1. It has to be piecewise, a piecewise defined function, of course. It's x plus 1 if x, yes, or, you're right, less than 2 or greater than 2. Or in other words, everything but 2. And if x is 2, what do I have to have in order for this function, with this new function g of x that uses f? I'm using everything I have in f, but I have to make a correction. What will be the correction?
3.
Exactly 3. Exactly 3. Why? Because the limit from the left and the limit from the right are 3. Therefore, the function value at 2 has to be 3 for the function to be continuous everywhere. And this will be continuous, guaranteed continuous everywhere. Let's explain this again because I think not everyone was able to follow this. Okay, so let's review this from the beginning. We were given a function. I'm given this function, the first thought is domain, always. I see that x minus 2 is in the denominator. Obviously, x cannot be 2. I stated this restriction first. Then I factored the numerator. I realized that this factor goes away, and the simplified form is this. So this function is x plus 1, comma, if x is not 2. I said to myself now, okay, they say that this is a removable discontinuity, but I have to convince myself that the limit from the left and the limit from the right of 2 are both equal, exist, and they're equal. And yes, the limit from the left of 2 from x plus 1 and the limit from the right of 2x plus 1, they're both 3. And of course, they're not equal f of 2 because f of 2 does not exist. Function is not defined at 2. And then we were asked, okay, use what you have, but create a totally new function using function f that will be whatever you come up with, guaranteed to be continuous everywhere. So I used the function that I was given, f of x is x plus 1 when x is not 2. And then I said, I have to fill in that gap. That was the only gap at 2. But since the limits left and right are 3, the only value that fills up that point must be 3. So the graph was this before. It's x plus 1 when x is 0, y is 1. When y is 0, x is negative 1. And at 2. This was the graph of function f. Sorry. This was function f. The limit from the left is 3. The limit from the right of 2 is 3. The only thing I can do is fill this in with a 0.2 comma 3. And now I created function g that is continuous everywhere. That was the only chance. And this was 27, and you have to do the same thing for problem 24 on page 128. This was what we just did, a problem before. We learned how to determine different parameters or parameter in order to ensure that the function is continuous everywhere. And I said this is extra credit because it involves a little bit of work. It's not as simple as the example that we looked at. So this will be extra credit for you. Any questions from me? Okay, I'm going to ask you and let you choose. Would you like to work on some other problems now, or can we start limits at infinity? Is there a particular type of problem that you would like to go back to, or you would like to continue with the limits at infinity? What would you like to do? Do you want us to stop and work on some problems? Okay. Any particular type of problem that you would like to look at? Any particular type of problem? Or would you like me to choose?
Are there any with absolute value?
Yes. Yes. Let's look at something. I'm looking at the end of the section, and let's see if there is anything with absolute value. And I'll ask you if you'd like to choose that. So there is one with absolute value here. Use the intermediate value theorem to show or find that there is a root somewhere, if you'd like to do that more. Any other limit that you want to look at? We can look at problem 20. It's an interesting problem. I have not shown you these limits just yet, and there are limits at infinity, and I don't want to do just that because this is in 2.6. Again, this is a limit at infinity. I don't want to do that just yet before I present in class. So what would you like to do? Let's not waste time. Let's find something. You want to do 10? Okay, perfect. So let's do 10. Good example. Perfect. So, and this is problem 10 on page 167. So we have limit. I will replace v by x because it's easier to write and easier to follow. Good pick. Thank you, Robbie. You're right. We should have done more of these. Did you have any difficulties with the problem in the limit document? There was an absolute value there. Would you let me know by Thursday if you have any questions on that problem? Okay. Very good. Where is my starting point? Very good. Very good. Yes. Normally, I would say yes. However, I need to simplify this first. So my starting point has to be 4 minus x in absolute value. What are the options for 4 minus x? Very good. So first one is 4 minus x. If do not solve it, I just want everyone to see what we're writing. Just tell me what to write and we'll solve it in a minute. If I have to write what is less than. Do not solve anything. I just want everyone to see. You're way ahead of me, which is fine. Okay, we're not sure about the definition. Okay, let's write the definition. Any expression in absolute value is the expression if the expression is greater than or equal to 0, and it's the opposite of the expression if the expression is less than 0. All these have to be identical. This and this and this and this and this have to be identical. So when you dictate to me, please dictate the identical expression. I'm ready. If is greater than or equal to 0. Good. Then
Or negative.
Very good. In parentheses for now, so where everyone to see. Very good. If. Awesome. This is the starting point. For any expression in absolute value, I have to fill this in. Yes, this is not done. So let's continue. So I have the absolute value of 4 minus x, which is 4 minus x if, and now I have to solve this. I will move forward to the other side. I get negative x greater than or equal to negative 4. But what do I need to do now? Yes, so what will happen here then? If x, awesome, awesome, good. Now leave this as is. Do not distribute. You'll see in a moment why. If, here's the point I'm trying to make now for a moment. Please watch this. Do not ever solve this inequality. Never. Do not bother with it. Do not spend time with it, and you may still make a mistake. Please do not. If this is less than or equal to 4, what should this be? You don't have to look anywhere. That's it. Do not solve the second inequality. You may forget to switch the symbol. Who knows what happens? So the second inequality never ever needs to be solved. Good. As you've noticed, our function is only this piece. What we just did is only this piece, but the function is this piece, the whole thing. So now I'm ready to write 4 minus x over the absolute value of 4 minus x. What is the first possibility? When this, which is here, is this, what do I write? Over. But I already have changed it. So this quantity can be this or this. If it's this, what do I get? Exactly. If, careful now, I cannot write the equal symbol. Why I cannot write the equal symbol on this inequality? Because the absolute value of 4 minus x is in the denominator now. And that's not allowed. 4 is not allowed. What is the other option? What is the second option? When this quantity is this quantity. Very good. If that's it. After all this work, now I know what this represents. Limit as x approaches 4 from the right. From what? Exactly. And what is the limit? The limit of a number, this is a limit law, -1. Who cares where x is going? The limit of -1 is -1. Okay, do we need to redo this problem? Let's do that. Okay. So we were given this function 4 minus x over the absolute value of 4 minus x. First, I have to start with this because I don't know what it means. So the absolute value of 4 minus x is 4 minus x if 4 minus x is positive, or negative 4 minus x when 4 minus x is negative. So far, so good? So therefore, this function has two options because this quantity has two options. This quantity simplified here is 4 minus x if x is greater than or equal to 4. Less than or equal to 4, and it's -4 minus x if x is greater than 4. One more time, because this quantity has two options, this expression has two options. Here's how. 4 minus x cannot be changed. This one has two options. If I have 4 minus x over 4 minus x, I get 1. If I have 4 minus x over the opposite of 4 minus x, then I have negative 1. Is that clear? So 4 minus x over this one, which is 4 minus x, I get 1. 4 minus x over this one, negative 4 minus x, I get negative 1. So far, so good? Do you see that? It's okay if you say I don't, and I'll explain again. So the reason why here I had the equal symbol is because this is not in the denominator. The reason here I don't have the equal symbol is because this isn't in the denominator. So obviously this function is not defined at 4. It cannot be defined at 4 because the denominator will be 0. So finally I look here and it says find the limit as x approaches 4 from the right. 4 from the right, the entire function simplifies to negative 1. So the limit of this as x approaches 4 from the right is basically the limit of negative 1. Therefore, the answer is negative 1. What if I ask you what is the limit of this as x approaches 4 from the left? What if I ask what is the limit from either side? Does not exist. So the difficult part here was simplifying the absolute value. If you would like to choose another, we can also look at the one from the, I don't remember if we did this. I don't think we did. Okay, what if we do this one? Please always remember to review all these on daily basis, all these limit laws and limit examples, because that's exactly what you are going to see on the test. Okay, good. So let's look at this, and this is limit as x approaches 0 from the left, 1 over x minus 1 over the absolute value of x. So please tell me, where is my starting point? For sure. With? I cannot add these. I cannot subtract. The absolute value is a very special quantity, a special expression. I will not be able to add and subtract anything that has absolute value in it with x in it. Awesome. Thank you. So I have to start with the absolute value of x. What are the options for the absolute value of x? Right, so the first one will be comma, awesome. The next option, negative x, comma. Very good, awesome. Now I'm ready to work on the entire function. How many options will the entire function have? Very good, because the absolute value has 2 options. Good. So the first option, please follow through. 1 over x minus 1 over? Good. How much is 1 over x minus 1 over x? Because I replaced the absolute value. So what is it? Awesome. For x, very carefully now. Just greater. Awesome. Well done. What is the other option? Careful. 1 over x minus 1 over negative x, but there is minus and minus. What do I get? Yes. So 1 over x plus 1 over x. An apple plus an apple. 2 apples. Comma. X less than 0. Now I know exactly what the problem is asking me to do. I'm asked to find the limit as x approaches 0 from the left of what? Very good. Remember, this is a function that I asked kindly to commit to memory. We need to remember this graph. If it's 1 over x or 2 over x, it doesn't matter, the same shape. So, what is it? Here's the graph of 2 over x or 1 over x is the same thing. Very important to remember this function, please. So the limit is? Awesome. The limit is indeed negative infinity. What if I ask you what is the limit of this function as x approaches 0 from the right? 0. What about the limit of this function as x approaches 0 from either side? So please remember we cover that as well. I don't think we did problem 5, did we? I will stop here. I know you're tired, it's a lot. But we did not do this one, correct? No, so just remind me to. So we did answer the greatest integer function, however. Okay. Thank you for coming.